Okay, so now we're going to talk about percentiles. It's going to be our last descriptive, well, one of our last descriptive stats, but it's a very useful statistic. And the value of it is it allows you to take into consideration, describe a score using information from the mean and the standard deviation. And we're going to see in a sec that those two pieces of information together are critically important in certain circumstances to kind of describe, for example, a person's performance on a test. Okay. This is the scenario. A child comes home with the results from the province's standardized test for grade 6 math and English. The parents read the report and see that their child scored 76 on both tests, and the mean for both tests was 70. So the mean was 70, and the child got an identical score of 76 on both tests. And the question is, did the child do equally well on both tests? So this is a provincial standardized test. The population, this is a population, all the kids in grade 6 complete both tests. And the question is, the kid is 6 points above the mean on both tests. Did the child do equally well on both tests? Well, the answer is actually going to be no. But I really can't answer the question because I need one more piece of information. The standard deviation. That's the amount of dispersion in the scores. The child did not do equally well on both tests. And the reason is, same score, 76, and the mean 70 for both tests. But the amount of dispersion for the math test was a lot less than the degree of dispersion for the English test. A standard deviation of 3 means the scores are closely clustered to the score of the mean of 70. With a standard deviation of 12 for the English test, that means the scores are more dispersed away from the mean of 70. So the child actually did far better on the math test relative to his or her peers than he or she did on the English test. On the English test, with a score of 76, you're closer to the average, whereas with a standard deviation of 3 for the math test, a score of 76 puts you in the top bracket in terms of performance on that test. So I need a descriptive stat that takes into consideration both the mean, the standard deviation, and the scores. Okay. Looking at the test. So the scores are normally distributed. That's our typical bell-shaped curve. And the mean is 70, standard deviation of 3. And as I can see for the child's score of 76, that child's score is out on the outer tail on the right side of that normal curve. So that's a fairly exceptional performance. And the N is 350,000 kids completed that test. And this is here my frequency distribution across all those scores. When I look at the English test, same score, 76, same mean as 70, but because the scores are more spread out, the child's score is much closer to the mean. Now this is a bit deceptive because the shapes of the curves are the same in both slides, but the difference is, if I look at the range of scores for the English test, the scores range from 10 to 129. If I look at the math test, the scores range from 55 to 85. So it's a bit deceptive. The curve is the same shape, but the amount of spread on the x-axis is far greater for the English test than for the math test. So just to make sure the curves are not the same. So the child clearly did better on the math test than on the English test. And I need a metric, a descriptive stat that tells me that. And I want to send that home to the parent because I don't want to send home to the average person that, well, your son or daughter scored 76 on both tests and the mean of 70 for both tests. But, dear parent, the standard deviation for the math test was 3, and the standard deviation for the English test was 12. So you go out and figure out the percentile. That's not going to happen. So oftentimes, standardized scores, you're often going to get your percentile rank as a descriptive stat. And that's what we call the percentile. And then the percentile is the percentage of scores below a given score. Okay, and our distribution is normal. Okay, the normal distribution. The normal distribution in terms of the shape of the dispersion of scores, in terms of that bell shape, where most of the scores are clustered around the mean, and as you get away from the mean to more extreme scores on the lower end, and the higher end, the number of cases becomes much smaller, and it diminishes right off. So it's that, as I say, the bell-shaped curve. The chart on the left is for the annual rainfall in Edinburgh, Scotland, in millimeters of rain across the last 100 years. And as I can see, the amount of rain that Edinburgh, Scotland gets on an annual basis is normally distributed. And I can also, important piece of information we'll get to later, is that for any normal curve, the mean is equal to the median, which is equal to the mean. So 50% of the scores are below the mean, 50% are above. And that's because the mean and median are synonymous. It's the same score. In psychology, intelligence scores, test scores are typically normally distributed. And in the physical science or the health sciences, diastolic blood pressure is in the general population is normally distributed. Now I want to figure out the percentile for my math and English test scores. And to do that, what I would need to do is I would need to know the equation for the normal curve, this equation here, and then I would have to know integral calculus to get the integral to figure out the area under this curve. And I'd have to do that for every percentile I wanted to calculate. So I'd have to know pretty advanced math to be able to do that work. Well, thankfully, statisticians and mathematicians have made this a lot simpler for us. And what they've done is they've created a table that across a wide range of scores, it'll give you the percentile rank for a given score. And to do that, and to focus it on one table, because they can have multiple combinations, of mean and standard deviations, they use the standard normal curve. And the standard normal curve has a mean of 0 and a standard deviation of 1. And we know how to calculate that because when we belled the grades last week, the first two steps in belling the grades was to generate the z-score, or the standardized score. And whenever I take a distribution and create standardized scores, I end up with a mean of 0 and a standard deviation of 1. And that is always the case. And that special calculation is called the z-score. It's the standardized score from a distribution. Now, I know by definition that if I calculate the z-score for all the scores in a distribution, by definition, the mean will be 0 and the standard deviation will be 1. So that makes the standard normal curve quite useful. So I don't have to calculate it for every score in the distribution because I already know what the outcome is. The outcome will be a mean of 0 and a standard deviation of 1. But what I can find out is for that distribution as a mean of 0 and a standard deviation 1, what is the z-score for a specific score? So in this case, I want the z-score for the score of 76 for the math distribution with a mean of 70 and a standard deviation of 3. And I want the z-score for the English test scores with a mean of 70 and a standard deviation of 12 and a score of 76. And I will calculate the z-score for each of those. For the math test, to transform it into put it on the standard normal curve, that score of 76 with a mean of 70 and a standard deviation of 3, on the standard normal curve with a mean of 0 and a standard deviation of 1, the z-score for, in this case for our 76 on the math test, the z-score is 76 minus 70 divided by 3, which is a z-score of 2. Similarly, I do the same for the English test scores. So I take 76 minus 70 and I divide by 12. The z-score for the English test is 0.5. So looking at it in a slightly different way, as for the math test, the kid scored 2 standard deviation scores above the mean, right? Because the standard deviation is 3. 2 of those units, 3 times 2, would take me to the 76. In contrast, for the z-score for the English test of 0.5, they're only half a standard deviation unit above the mean, 0.5. So as we see, for the English test, slightly above average, but for the math test, quite exceptional, right? Up in the upper tail of the curve. Now that I've got the z-scores, the statisticians and mathematicians did all the heavy lifting for us, and they created a table across a range of z-scores to figure out the area under the curve to get the proportion. Because the area under the curve represents all of the people. And the standard normal curve has it such that if I can figure out the z-score here, the area under the curve as a proportion of the total area will be the percentile rank. Okay, And the score that we use is the table that we use is the one generated by the mathematicians and statisticians for the standard normal curve. And what it does, across a range of z-scores, it'll tell you the area under the curve from the mean of 0 to that given z-score. They did this because it's just it gives you more flexibility if you're doing it by hand. And what it does is, because we know that because the median and the mean are the same, the proportion of people below the mean is always 50% or 0.5. So I know this area under the curve here is 0.5. Half the people are below the mean. If I can figure out the area in the blue shaded area here, and I add that to the 0.5, that will give me the percentile rank. And that blue area under the curve, the proportion of people from the mean to the given z-score is in the body of the table here. And we'll walk through that for the math test and the English test. Okay, for the math test, the z-score was 2. So I'm just going to use the column here. I find the z-score of 2. First column here. The proportion of scores between the mean of 0 and that z-score of 2 is 0.4772. Of all the people in that distribution, 47.72% of them are between the mean of 0 and the z-score of 2. I know that half the people are below the mean. This is 0.5. So I take the 0.5 representing the people who are below the mean, add to it the 0.4772, the percentage of people or proportion of people between the 0 and the z-score of 2. I add it together, and that gives me the proportion of people who scored lower than 2 and had a z-score lower than 2. And that proportion of people is 97.72. So 97.72% of the people who took the math test in grade 6 scored lower than 76, because that 76 equates to a z-score of 2. Similarly, for the English test, z-score of 0.5. I look up in the column here, I look up the 0.5, and I see that the proportion of scores that are between the mean of 0 and the z-score of 0.5 is 0.1915. So 19.5% of the scores are between the mean of 0 and the z-score of 0.5. I add that to 0.5 to get the percentile rank. So the percentile rank for the English test for that child is 69.6915, which means that 69.15% of the kids who took the test scored lower than 76 on that standardized English test, which equates to a z-score of 0.5. So the percentile rank for the math test is 97.72. So I would tell the parents, well, your son did or daughter did really well, scored in the top 2.28%, so you're right near the top. Did well on the English test, but was only in the 69th percentile. 69% of the kids scored lower, but on the math test, roughly in the 98th percentile. Did much better on the math test than the English test. And one lump sum, and one with 2 scores, the 2 percentiles, I basically are telling the family